be the place that if you are wanting CE credit for this, that will be, we need you to reply there with just your name and your email, because again, unfortunately, all of these technology woes, someday you're the windshield, some days you're the bug. Today we were the bug. And we don't have access to all of your guys' individual information of who attended what schedule or what session, excuse me. So we will need that from you folks. It looks like we hit about 50 people, and that's usually where I've been seeing it land. So I'm going to go ahead and start. Moose, if you want to hit the recording, and that way we can just get everybody going here. Luckily, this is another one of our shorter ones, BAS 103. We'll just dive right in together. So you've seen 102 and 101, and this is the next one in the series. We'll focus on controller selection, mechanical equipment, and sensor control. As we have seen, we are an AIA continuing education provider. So that is just what I was saying there, that if you need those, we will be sending out a survey and would love for you to respond to that in order for us to get that certificate out your way. Copyrighted materials are being presented. Without further ado, so this is just our basic agenda. I want to go through and actually talk a little bit about what we've seen so far in this series, but just a quick review, choosing controllers, talking about VAVs and AHUs. We'll explain all of those acronyms and actually go into chillers, boilers, whether they're air-cooled, water-cooled, and then finish up with sensors and control and actually do just a very brief introduction into sequence of operations. So we've seen this before, right? Our BAS series. We still have that big old question mark there. We're leaving you guys on the best cliffhanger. I know you probably won't be able to sleep tonight, but we're going to start out tomorrow strong with BAS 104, and that will really be around sequence of operations. But what we've seen so far in 101, we talked about the overarching why do we need a BAS? What does it do for us? Some of the challenges, some of the benefits that you can experience with that. Moose then took us into 102. And that was around all of our points and protocols. So what is actually being controlled? We talked about inputs, we talked about outputs, we talked about control loops and protocols and how all of these things are talking together. So now we're here, we're at our interdependent systems. And what we're calling this is a lot around the mechanical systems. And basically what we're going to do here is we're going to talk about the fundamentals of each of these systems and how that actually interacts with building automation, covering, like I said, VAVs, AHUs, boilers, chillers. But what we're really focused on here is how that interacts with a controller. So how that is being controlled by our BAS system. So keep that in the back of your minds as we go. Now, when we did define that BAS system, what we basically boiled it down to within 101 and 102 is around this need for a centralized system that can not only control and monitor, but also optimize our HVAC, lighting, our entire building system in general. And what we're really going for there is around the energy efficiency and occupant comfort. So you're going to hear me say those about 5 or 6 more times throughout this presentation. But that's really what this system in general boils down to, is how do we get that balance between our energy efficiency and our comfort of occupant, and how are we going to control that in our space? So our key components here, what we're going to include are going to be variable air volume boxes. So that's what I kept saying, VAVs. We're going to learn about chillers, boilers, and air handling units, and how all of these are kind of interconnected, what the roles of sensors and actuators are within these systems. And we're going to bring that together there to include that interconnectivity of components. And what we're really building towards is getting everybody to a point of being able to create a sequence of operations. So in order to do that, we need to know how all of these systems are functioning together to get to a point where we can have that points list, we can have that schematic, and then we can have that sequence of operations to build a functioning BAS system, right? So with that, let's start first. I know in 102, we kind of left you on a smidge of a cliffhanger around controllers. Moose kind of brought us home there with, there are a few different types of controllers, but let's talk about that a little bit more in depth. So in building automation systems, our coordinated control logic is really essential to being able to manage all of these complex interdependencies that are in between, like VAVs, air handling units, chillers, and boilers, that mechanical equipment. So all of this logic is what's going to ensure that each component is operating in sync. And this is going to give us that balance between performance and energy efficiency. Again, we talked a little bit about control loops in BAS 102, but just to remind you, and then to put that in the context of how this works in play. So it's going to be a control loop in a building automation system is going to be this automated process that's actually regulating specific building systems or components by maintaining your desired conditions. And what we talked about on desired conditions in 102 was going to be kind of your inputs, right? So that's going to be your temperature, your humidity, your pressure, those sensor-based control pieces. And then that typical control loop is going to involve three key components that we talked about. That first one is going to be your sensors. That's going to be what's measuring your current condition inside of your zones. So again, your room temperature, your occupancy. It's then going to have a controller. So that controller is what's going to compare our input or our sensor number into it's going to compare our sensor into a predefined set point. So it's actually comparing what you have in the building compared to your set point. And then that third component of your control loop is going to be an actuator or something that is adjusting the system output to minimize the difference between the measured condition and the set point. So basically what we're trying to do is create the set point that we want in each of our zones, and we need to know how to get from point A to point B. Like Moose took us through, these loops can operate both in open loop and closed. So open is just going to be that no feedback. Closed is going to be more feedback driven configurations. Closed loop is going to be able to provide that continuous adjustments for a little bit more precise regulations. So what we have on here is our example control loop. So in real life, what this looks like is, say, in a certain zone, so in a particular room, a VAV system is going to signal to our air handling unit to adjust the supply air. This is going to trigger that control loop. And what that's going to do is it's actually going to modulate airflow, and it's going to create that temperature dynamic change based on real-time data to meet that demand, to meet that set point without wasting energy. So all of this coordination and what we're talking about here within controllers, what's really key here is to be able to maintain that comfortability and that efficiency. And that is what your BAS system in general is doing. So this is why control is really important. And again, that control loop there, if those words don't mean much to you yet, they will soon, because we're going to go through how each of these really interacts with each other. But when we talk about controllers, what are we really talking about? So for our purposes, we're going to focus specifically on bacnet controllers. We've talked about this before. Bacnet is just the building automation control network. But how are these really being defined? So there is a bacnet testing laboratories, and they are an organization that is going to ensure the proper implementation of all of our bacnet products. What they're doing here is they're actually providing this industry standard test suite. And they actually issue certificates to manufacturers that pass all of these independent tests. So you can see there on the left where we see device testing and internal testing. That's done by the manufacturers. So manufacturers, all of us, we're actually going through and doing all of this pre-testing using all of the BTL resources, and then we submit it to a recognized bacnet testing organization. They're recognized, but they're third party. Then what this is doing is they're actually taking it through a bunch of different tests. And what the bacnet system does is it's defining all of these device profiles, which are going to categorize our controllers based on their capability. And the way that they're doing this is that each one of these device profiles are going to specify a minimum number of bacnet interoperability building blocks. So those are what we all know as BIBBs. So this is a specific number, it's a minimum number that the device must support, and it defines what those capabilities are. And it also defines the interoperable capabilities between each of these device profiles. We'll talk a little bit about BIBBs in a minute, but just know that this is actually what they are using to create these device profiles. And then once they go through all this testing, they get approved, and you do get the certificate. And you actually can go on BTL's website, BACnet's website, and actually see the different manufacturers and how each of their controllers are laid out based on the device profiles. And I think one of these in here, actually the device profile, that does click a link to it. So when you get these slides, that'll go directly to BACnet's website. So that way you can see kind of what's happening behind the hood, if you will, in BTL's website. So those three different device profiles, what are they? I say these three because that is normally what we are looking at. So the first one there is going to be building controllers. So building controllers are going to be that high level controller. It's going to manage and coordinate multiple different building systems, a lot of centralized control. It's going to be able to optimize efficiency across the facility. Next level down, we're looking at advanced application controllers. So this is going to handle a little bit lower down. It's complex applications such as HVAC, VAVs, air handling units, but it does have a little bit more advanced function, but it's still for targeted control. The final box down there, it's going to be your application specific controllers. So these are actually going to be designed for specific tasks. So think something more localized control like individual devices, pumps, fans, lighting fixtures. These are going to be what really simplifies operations with a user-friendly interface for direct control of individual components. Oftentimes we see that like application-specific controllers are going to be a cost-effective solution for these standalone systems that don't really require that bigger level of centralized control. So when we're thinking about which one we should use and which different application, looking specifically between building controllers and the application controllers, the biggest word that I like to use here is just scalability. So your scalability is going to be much, much greater on a building controller than an application controller. So that is really what they're built for. It's ideal for managing multiple building systems. If you need the potential growth, they can integrate with other devices without reconfiguration. And that's just not usually the case on the scalability of application controllers. So your scalability needs for application controllers, it's generally going to be a little bit more limited. They can be scaled within each subsystem to expand coverage, but not in the same way that a building controller really can, be expanded if you're going to grow your entire building. We talked a little bit about the BIBBs, those bacnet interoperability building blocks, and this is by no means a breadth of categories here, but these are just a few that I picked out from the BTL website between the three different categories. And again, this is what's really shaping those device profiles. So something that's in a bacnet building controller might be something like the ability to share data between multiple different controllers, or you might not need that in an application-specific controller. Now, these are what's going to really start to frame up as we start thinking about specifications and as we start thinking about, building into that real BAS system. These are what's going to be listed in your specifications. So if you know that something in your system is going to need a specific property here, a specific BIBB, those would go in your specifications to make sure that you're choosing the appropriate controller. Now, we don't want to get like too specific into choosing controllers because, again, this is more along the lines of that industry and manufacturer agnostic. So when we really start diving into the specifics, it does get a little bit manufacturer heavy, specifically when we're starting to talk about division specifications and how you would actually go in and choose a controller. So we do have those resources available. So just know that like when you're actually going into choosing a controller for a project, we definitely can help with that. The idea here is just that overarching, hey, here is the difference between these controllers. So if we've gotten to this point and we now know whether or not we want a building controller or we want an application controller, advanced or specific, what do we really need to start thinking about? And this is what I was talking about, where it really does start to vary from manufacturer to manufacturer. And when you really start diving into the depths of controllers, it does get a little bit brand heavy, if you will. But the couple things to talk about and what we really want to think about here, Moose took us through a few of these in BAS 102, right? So compatibility, network support, and protocol support. That's all going to be around how this controller is going to talk to the system as a whole, right? So how this system is going to interact with maybe what's already on the building or maybe those components that we're going to talk about next. You really have to start thinking about, like Moose had that diagram of all of our network infrastructure, how these are going to be talking to each one of our different components. So, if you're using a network that is an Ethernet network, you're going to want to choose a controller that supports onboard Ethernet, right? Or have a plan to get that controller talking on an Ethernet protocol. Again, we talked a lot about bacnet. We talked a lot about bacnet secure connect. If you want that extra security, make sure you're choosing a controller that supports that. And that final point there, actually, it's not the final point, the point that's in the middle. The point that's in the middle there is about the inputs and outputs. And that was, again, what we talked about in BS 102. We got you all the way to the point of being able to build that points list up as an engineer. So once you have that, you know how many points are going to be included, especially the real. Moose took us through virtual. That's not really super applicable here. But the real IO points that you're going to need to physically wire up to that controller. If you have 6 IO points, 6 inputs, and 4 outputs, you know that you're going to want a controller that can actually handle that much input output. Or if you need excuse me, add-on modules for that, just a way to start sizing your controller based on what you are actually controlling. So that's just a very brief overview when it comes to what controller selection actually looks like. And again, we'll start to see what all of these controllers are controlling. And so what are typical applications? How many inputs and outputs are you going to start to see? Can we start to build those points lists for each of these systems that we are going to be controlling? So we're going to shift gears a little bit and we're going to head into our mechanical equipment and sensor control. So our first one on here is going to be our VAV systems. So our VAV systems are going to be, sorry, somebody's just walked in on me here. Apologies, guys. So we're starting with our VAV systems, and they are designed to provide precise temperature control by regulating airflow to specific buildings and to specific zones within each building. So basically what's happening here is that the volume is being adjusted throughout our air supply to maintain comfort in multi-zone buildings. The main components of VAV systems are going to include our VAV boxes, which are going to have dampers, reheat coils. That's going to work with supply fans, all working to control our temperature and airflow in each of these designated areas. Let's look a little bit what's under the hood of one of these VAVs, what it actually looks like. So on the left here, you'll see what a VAV box itself looks like. And then on the right, we have a diagram of what's going on inside of a VAV box itself. So let's look at the one on the right here and talk through what we're seeing. So as we go from left to right, we're seeing first our supply air duct. So this is actually where the air is being brought in from the conditioned system. Next, we're going to see a damper. So a damper is what's actually going to control how much air is being let through. An airflow sensor is what's going to monitor that rate of airflow. And then an actuator is what's actually going to move that damper. So actuators in general are going to be the pieces that work by receiving a control signal. So when we talk about our controller, that controller is going to send a signal to the actuator. And that actuator is then going to use an energy source to create that mechanical motion of our damper. And we'll see how that works. Our reheat coil there at the end, this is optional, but it can add warmth if it's needed. It's being supplied by our hot water control valve there on the bottom. And then finally, we have a temperature sensor. So that temperature sensor is actually going to be sitting inside of a zone that is controlled by the VAV. So that temperature sensor is the one that's sitting there and it's sensing the environment of your building, signaling to the system whether or not it needs to make adjustments. So we talked very briefly about that control loop and what that looked like. So let's rethink about that, right? So when a thermostat is sensing a change in a room temperature, it's going to send a signal to the actuator, and then the actuator is going to open or close that damper. Usually we see that from about 30 to 100%, which is what will actually adjust that airflow to bring in more or less cool air to the zone as needed. Now, if it's cooler weather and we actually want to heat something up, that reheat coil is going to step in. So our hot water valve will open, the reheat coil will heat, the air is actually going to flow across that reheat coil, and that's what's going to bring the temperature up in the space. So that's just kind of everything in general when we're looking at a VAV box. There are a few different modes of operation. Now, I should say that these modes of operation are really for traditional VAV control. Again, I love to give you guys cliffhangers. So we will talk about some VAV strategies that are new in the Guideline 36 presentation tomorrow. So get super excited for that. But for right now, we'll just think about traditional VAV control. We have 3 basic modes. So we have our cooling mode, our deadband mode, and our heating mode. In cooling mode, our control valve of our hot water heater is going to be closed. And that's where that VAV box damper is going to be open anywhere from 30 to 100%. So if you want more air being thrown through there, you're going to open that damper to 100%. That way you're getting more airflow. Our deadband mode, this is important to talk about because our deadband mode is there for when there's really no need for heating or cooling in the space. So we have that temperature sensor, we have a set point, our room is fine, we're all just chilling, we don't need to cool down, we don't need to heat up, but we do have to meet our industry standards. We talked about these industry standards in 101, and I have a slide on them as well here in about 2 slides. But just keep in the back of your mind, there are ventilation requirements. So even if heating or cooling isn't necessary, we are still going to need to be moving through that air for ventilation requirements. And then heating mode, obviously, it's just when that reheat coil is engaged, our hot water control valve is open, and you're getting that air pulled through across that reheat coil, which is heating up the space in order to satisfy the requirements of that space and get that set point back to where it needs to be. A couple of different types of VAV boxes you're going to see. For our purposes, these basically all are going to function the same. Again, we're thinking in the minds of a controller. We want to know what we're controlling, but just so you guys know, you're aware what you might see out there. Single duct, this is probably going to be the simple and most common, can be configured, like we said, as cooling only or with reheat. We also have fan-powered dual duct terminal VAV boxes. It's going to take advantage of having 2 ducts, one for hot and or neutral, and then one for cold. And then finally, you can see induction terminal VAV boxes. This is just going to be induction principle instead of using a fan to pull in that warmer air. But what's really important here is, again, how all of this is working together. And we have this kind of crude schematic here, but I think it's really important to look at how all of this is actually working together. So bear with me as this slide builds. So what we're looking at here is essentially 2 systems working together in tandem. So the first one is going to be our air handling unit that is working on a system level. So what's happening here, like I said, is it's starting by pulling that outside air and conditioning it. So this is then what's going to condition, see how cute that was? And then it's going to be pulled in through our supply air duct. So this is what's actually going through, and then it's going to enter our VAV boxes. And this is actually getting triggered by our zone level. So again, we have these set points in each one of our zones, and we want to maintain those. And so what we're doing is that when something is out of that set point, you're getting a request, and that request is going to say, hey, we need more air in zone 1, or we need less air in zone 2. And what that's going to do is it's going to dictate how much air is actually going through that duct, right? And then obviously what we have here is then the return fan, and then your air gets sent through. But what's important to note here is that what's changing is just the amount of airflow to and through those VAV boxes to the zone. So basically what they're doing is they're regulating the flow of CFM based on what the zone is calling for. And the way that this is actually done, you see in there in that little box in between where it says 1 and 2, we have a couple of different sensors. And Moose took us through what those sensors might look like as far as inputs and outputs. But in this scenario, we have one that's a duct static pressure switch. So if you're getting a lot of air flowing through there and you know that your zone is calling for even more air, what's going to start to happen as the pressure increases or decreases, so we're always going to be monitoring that static duct pressure. If it sees a change and it says, oh, hey, my pressure has decreased, I need more air, this is what's going to send a signal to the VFD to ramp that up, to say, hey, we need more air flowing into the zones. So really what this is doing is all of this is working together, and it's really being controlled by the brains of the operation, which is that controller. So all of this is really set in play. And what we've really just described here is going to be our sequence of operations. So we're getting to that point where all of these are starting to work together in order to maintain that energy efficiency, but also occupant comfort at our zone level. So the way that this looks in real life, so that way it's maybe just a little bit better than our crude rudimentary drawing there, it's going to be 2 different zones. It's the exact same thing that we just looked at. So we have our zone there on the bottom left, which might be a high load zone, right? So what we're seeing there, there's a lot of people in there. Maybe they're having a party. Our gent there has some his open window on a hot day. So what we're getting is we're getting our temperature maybe too high, right? We want to continue and maintain that temperature in that zone at 55 degrees, but man, oh man, it's just getting too hot in there. So what's happening, you can see on there that the VAV box is fully open. So that means it's pulling more air into the space. Whereas we might have our lovely gal up there in our moderate load that is saying, hey, there's no window, there's only one heat source. So our VAV box could be partially open, or it could even be in that deadband mode if we're right at that set point that we need to be in that zone. So this is really how all of this is working together in those control loops in order to maintain that energy efficiency and occupancy comfort. Now, when we're talking through all of this, Moose really brought us home to those points list in 102. And that is something that we always want to keep in the back of our minds because it's really what was going to shape into our units of operations and into our drawings. So what we're seeing here is just the sensor network. So a lot of our inputs that are going to come through our sensor network as far as what we're trying to monitor. So if we look on here, these are just a couple of them that I threw out here for you guys that we've talked through in our previous slide there. But you'll see, things like room temperature sensors, CO2 sensors, humidity sensors, occupancy. So occupancy is going to be one of those ones that is going to trigger something in everybody's minds after we're done here. I'm going to say, oh, occupancy, we might need to increase ventilation rate just because we have standards in play. And then the only other one that I really want to point out there is that static pressure switch. So just for, peace of mind, what everybody says is it should be located about 2/3 of the way downstream of the VAV. And that's what's really going to, pull in that air or slow down the air by the VFD. So again, that's by no means everything that you might be monitoring, but it just takes us to a good point where we can start to think about how all of these are working together in order to be controlled and what inputs and outputs we're going to have. I mentioned that we would look at this slide one more time, and this is what we saw in 101 around our industry standards. So our industry standards are, ever changing and ever adopting. Right now we have 62.1, and that's going to be that ventilation for acceptable indoor air quality. And so that's the one that I was saying, even though we might not need to change the set point in that space, say we're all very comfortable in that space, there is a set amount that needs to always be filtering through in order for acceptable indoor air quality. So again, when we talk about why do we need a BAS system? Well, we need a BAS system because there are standards in place. So even if everybody thinks that they're comfortable, we need to be able to meet all of these. And this is how we get from point A to point B. Now, like I said, there are more and more control strategies that are coming into play. And something that we are seeing now, it's called demand control ventilation. It's another way, like we were talking about, when we talk about VAV control, there's now some advanced operations, and one of these is demand control ventilation. So your ventilation rates are actually being modified in response to occupancy and indoor air quality. And what this can do is it can actually reduce unnecessary energy usage. But the way that all of this is happening is that it's basically with the air handling unit, supply fan, and the demand control ventilation, it's going to bring those two things together. Again, you're always getting your input from your duct pressure balance, but it's going to be a more precise and a more intelligent way to control those VAVs in order to match the occupancy use and still maintain your standards. So again, we're going to talk a lot about this in Guideline 36, but what I wanted to do here is just, again, get you guys in that mentality of thinking through how all of these systems are going to be coordinated together to always work through our controlled loops. So this is what's going to happen in Guideline 36. Keep it in the back of your minds, but it's just another more intelligent way of controlling our VAVs with our air handling units. That is the end of our VAV and air handling unit section. So now let's swap on into a boiler system. So a boiler hot water system is what is going to provide heat to a building by heating up water and actually circulating it through the pipes to radiators, air handling units, other devices And these devices are what's going to then release that heat into rooms. So this is going to be our system that is there in place in order to keep our rooms warmer. So again, always think about what is the end goal here. The end goal is our energy efficiency and our occupant comfort, right? So major components of this excuse me, major components of this are going to include your burners, heat exchangers. Your burners are actually what's going to be inside your boiler. It's going to ignite that fuel. Heat exchangers are transferring our heat to water. And then important parts of the system as a whole are going to be our circulation pumps. Again, like I said, the radiators, which are going to release the heat. We are going to have a pretty significant network of sensors and valves and control pieces in this as well. I like to give you guys a lot of anecdotes. So the way that I think about boilers is think about them like your stomach. So the boiler itself is going to be like your stomach, right? It's burning all of that food in order to create heat in your body. The same way the boiler is going to burn that fuel to create heat. You're going to have your hot water pumps. That's going to be like your little heart. It's going to be circulating that blood through the body, just like our hot water pumps are going to be circulating that hot water through the building. And then finally, you're going to have your radiators, which are going to be like your skin, right? Your skin is used to release heat into the environment. And all of this is being controlled by our little brains, which are deciding when we need to eat or when we need to move, when we need more blood to be pumping, when we need to heat things up, right? So all of this is kind of the same way I like to think about a boiler. A little bit kitschy, but again, it just kind of helps you when you're starting to think through how this sequence of operations needs to go. You never know. You might think back to that crazy girl that gave you these anecdotes, and you'll be able to write a fabulous sequence of operations based off of this. Within our boiler system, we're going to have a bunch of sensors as well. I put this before our schematic because I want you guys to try and focus in on what's going to be our inputs, what's going to be our outputs, what we're really starting to track, and what we're needing to track, right? So in this scenario, we're going to have temperature sensors, whether those are on the boiler themselves, whether those are inside of the zones. But basically what we're doing here is monitoring the temperature of that water to meet the heating demands, while again, maintaining efficiency in our energy, right? We don't want this to just be cranking up and up and up, and we don't need it to be doing that. Pressure sensors, I know Moose brought up safety and pressure sensors. This is going to be a big deal in boilers because we do want to prevent unsafe conditions. Nobody wants to blow up a boiler. So again, you're just going to have all of these sensors along the way when we start to think about what we are controlling. A lot of this is in play when we think about our boiler system network in general. Now let's look at a little bit of a field diagram here. And what we're going to do is we're going to look at this kind of one step at a time in how our boiler system works. So the first place we're going to focus in on is actually the boilers themselves. So the way that the boiler is working, it's actually going to burn that fuel.
Elliot, lunch bag.
Say again?
Okay.
Oh, mute yourself. Something had lunch. That's okay. I want lunch too. Anyways, okay, so we're looking at that first part here, and that's where we're actually going to look into the boilers. So our boilers are going to burn fuel in order to heat up that water. Throughout all of these, we're going to have that sensor network, right? So that's going to monitor the temperature both inside the boiler as well as exiting the boiler. If that water isn't hot enough, what's going to happen is that the control system is going to send a signal to open a gas valve. Right? This is what's going to start to heat up that water more. You can also here have an igniter, which is going to light that burner to heat it up more. So the two ways there of how that water is actually being heated up. And then once that water reaches the desired temperature, the system is then going to set a signal to turn off the burner or to close that gas valve in order to save energy there. So again, start to think about we're controlling. This is all leading to a point somewhere, you guys, I promise. Our second step here is going to be in circulating the hot water. So basically what this is doing is this is using pumps and VFDs. So that's our variable frequency drive. We saw the same thing in our VAV and air handling unit. But what's happening here is that pumps are pushing all of that hot water through our pipes inside of our building into the radiators in order to release heat into a space. So as our water moves, it's going to carry all that heat to different part of the building, right? So what we're seeing here is going to be flow sensors. We're going to see pressure sensors, ensuring that all of our water is moving correctly into the room and into the zone. And then our final one here, it's not really pictured, but let's just pretend on there that we do have a couple of different zones within, excuse me, within those zones, we're going to see temperatures. So a thermostat in the same way that we saw it in the zones of our VAV and air handling unit. It's basically, it has a set point and it's saying, hey, the room is warm enough. The room isn't warm enough. If the room is too cold, again, it's going to start to open a valve. And it opens that valve to let more hot water flow through the radiator or air handling unit, whichever you're using, in order to release that heat into the space. And the important part about this too is that once that room is warm enough, once we did hit that set point, we need to build in something into our controller and into our program and into our sequence of operations that then tells that valve to close, so that we're not, heating up our guests and doing things that are going to just waste all of that energy. The final piece of this is in the bottom right-hand corner, our hot water return. So that's actually what is returning back to the boiler after the water has released all of its heat. It's already cooled down, it flows back into the boiler, and then the system just loops and happens again. So when we look at this is another, it's again the same type, it's just a little bit better of a schematic than our last one there. It's a little less rudimentary. But what I like about this one and where we are really starting to focus is we're starting to see a lot of these inputs and outputs, right? So when we think about our mechanical equipment in general, we want to take our zone, we want to take that system from, a set point of 65, and right now it's being measured at 55. So how do we get there? And the reason I like this slide too is just that way you guys can see kind of what are going to be our inputs, what are going to be our outputs, and what we need to start focusing on in order to make sure that we are getting that desired temperature in our space. So some of the inputs that you'll see on boiler systems in general, you're going to, like I said, have the temperature, pressure, and flow sensors, as well as your thermostats and, even your set points inside of those zones. And then you can also have things like your outdoor air temperature sensors here. And your outdoor air temperature sensor is going to be used for weather-based adjustments. And again, a lot of this, we're starting to talk into these advanced control sequences of maybe being able to do some predictive control. If we know it's going to be a really cold day, maybe we, like Moose said, put in a time delay. That's where you're going to start to have your virtual inputs and outputs, those virtual pieces of, okay, we're measuring the outdoor temperature with our outdoor air sensor, and it's really, really cold. We know work starts at 8 a.m. Let's put in that time delay to start at 7:50 to heat up our space. So again, all of this is just building to a point where we can start to control all of these systems in an efficient manner together. Couple of the different outputs that you'll see on here, your burner control, your pump control, and the reason, we see on here our boiler. We have our boiler status and our start boiler as two of our inputs and outputs. And again, that B in front just means that it's binary. So that's binary or digital, right? Those are two of the same, those two words mean the same thing. Moose took us through that. You're all pros at that by now. But basically, this is just saying, hey, we need to be monitoring whether or not our boiler status is on or off. And we need to have an output there for whether or not we need to start the boiler. So again, you can just kind of go through this diagram and see how all of these things are working together. You'll have a bunch of field devices in here as well. We have thermometers, pressure gauges. We talked about a few of those flow switches, as well as all of these valves that are turning on and off based on that control program that says, hey, we need more water or we need less water. Included in this as well, I know Moose talked about this, was safety devices, right? We need pressure relief valves, make sure to high temperature limit switches to prevent all of our equipment damage or even just unsafe conditions, right? So that's really all we're talking about here, is just getting to that point of now we have our points list. So that schematic was a really good one in order to build up our points list. So we can see on here, we talked about this before, we have our analog inputs, our analog outputs, our binary inputs, and our binary outputs. So what we talked about, again, is just the basics of a sequence of operation. But when we talk through, our controller, so now we have a set list here of inputs and outputs that we might need to actually be on a controller. So if we're going to use an advanced application controller to use and control this boiler system, we know that we're going to need 5 inputs and 3 outputs. So again, we start to think about, okay, let's now talk about selecting the correct controller for this application, knowing what we now know in order to heat up the space in our room, right? That was about it for boilers. So now we're going to switch. We just learned about how we need to heat up a room, but let's talk about how we're going to get that room chillier. And the way we're going to do it is with a chiller. So chillers are just what is going to design to cool the space, right? 2 different types. You're going to have air cooled and water cooled. We'll talk a little bit about that, but basically they both operate by transferring heat from the building to the outside environment. Primary components that we're going to see here are going to be our compressor. That's what's actually going to compress the refrigerant and increase temperature. Our evaporator, this is where the refrigerant is going to be absorbing that heat from the building's water system. Then it's going to go into our condenser coil, which is absorbing that heat from the outside. And then our pump is going to circulate that water back through the entire system. And that's where our expansion valve and metering devices come into play. So essentially, all of these components are working together in a refrigeration cycle, which is going to effectively manage that heat transfer outside of the building. I mentioned that there are 2 different types. And again, for our purposes, because we're really just talking through controls and figuring out how we need to change the temperature in a space or how we need to change something within a space. 2 different types here are going to be air-cooled chillers and water-cooled chillers. They are very appropriately named. Water-cooled chillers are going to use a water tower. Air-cooled chillers are not. Couple differences between the 2 of them. Like I said, obviously the biggest one is going to be the cooling method, water versus air. We generally see that water cooled are going to have a higher efficiency. They probably will be a higher initial cost just due to that cooling tower because you're going to have a lot of piping happening in there. Usually you're going to see this for larger buildings, more industrial applications. The applications on an air-cooled chiller is going to usually be a little bit smaller, and you might have a higher energy consumption in hotter climates with air-cooled chillers. But again, with water, you're obviously requiring water. So it just kind of depends on what you're going to be using and seeing inside of that building. But again, the important thing to notice here is just when you are starting to design that building automation system, this is yet another thing to bring up, whether or not, what is going to be on site, whether or not you know that, hey, they already have air-cooled chillers or they have water-cooled chillers. So now how do we bring these together in order to create that space that is both energy efficient and occupant comfort, right? So within our within our chillers, within our chillers, sensors and actuators, so our sensor network within chillers, basically, we're going to have a few things, again, very similar to before. We're going to have our temperature sensors. This is just what is monitoring the water in that heat rejection cycle or in that heat in order to basically monitor the temperature both in the cooling tower as well as on the water level itself. Your water level sensors, this is just going to track levels and maintain optimal operating conditions. Essentially, all this is doing is preventing low water scenarios. And then we saw this again, fan control actuators. Remember, when you think actuator, think, oh, hey, a signal is being sent to the actuator and something is being controlled there. And so this is just going to adjust that fan speed based on your cooling demand. So again, as we start to build this up, just start thinking through how some of these might be in our control sequence, right? We'll first go through an example of a chiller using a water-cooled system, so a cooling tower, and how this is actually working. So a cooling tower, it works with the water-cooled chiller to release all of that heat that is being absorbed through the building. So what's happening is warm water from the condenser barrel of the chiller itself is actually entering that cooling tower. Water is being sprayed over this fill material, which increases that surface area, and then air flows over it. And basically what's happening is it's evaporating some of the water, releasing that heat. The remaining piece of that cooled down water, basically this remaining water cools down as heat is actually being carried away by the airflow. And then that remaining water is recirculated back into the system to absorb more and more heat. So that's all that's really happening when you're looking at this cooling tower itself. Now, again, because we've seen how much I love anecdotes, And if you see my version of BS 102, I give you a couple more anecdotes in there as well. So if anybody's interested, just let me know. But we're going to think of another anecdote for a water-cooled chiller system as a restaurant kitchen. So if you think about it like that, the chiller is going to be the refrigerator. It's keeping all of its contents cold. So it's keeping the water cooler. The cooling tower itself is going to be one of those big exhaust fans that's getting rid of all of the heat from inside of this kitchen. The pumps within this system are going to be like our wait staff. They're running back and forth, bringing that water or bringing that food to and from the refrigerator to all of those tables. So think of that like the pump is bringing the water from that cooling tower to the zone, right? And then our air handling units our air handling units are going to be like our chefs. So our chefs are the ones that are delivering this whole experience to our diners. And of course, the person that is in charge of all of it, the head chef, making sure that everybody's doing their jobs, that's going to be your controller. So again, the brains of the operation, always going to be your controller. So when you think about a cooling tower, you never know, this might help. Love anecdotes. There you have it. When we look through what this actually looks like, again, step by step, let's build this together. So that way you can know kind of how we're going to go through and build our sequence of operations when we really start to look at all of this. So on the top here, we're going to have that air handling unit. So sensors here are going to be what measures, your room temperature, your humidity, your supply air temperature. When your room temperature is too warm, the control system is yet again going to send a signal to open that valve. It's going to say, hey, we need more cold water to be flowing into our air handling unit. Again, this happens by sending a signal to an actuator. The fan in the air handling unit is then going to blow air across that chilled water coil, which is actually what is chilling the air. So that's how you're actually going to get that cool temperature inside of your zone. This is all being controlled, like we said one slide ago, and I apologize, it's actually not on here, but this is all going to be controlled proportionately by that variable frequency drive. So that's going to be kind of what tells it to speed up or cool down how much air is actually needing to be pulled through there in order to get to that desired set point in our space. And again, another important piece of this is to make sure that once we reach that desired set point, we need to then close that valve to save our energy. Our second piece of this is going to be the chilling water itself. So going into a chiller control. So the sensors on the chiller are actually going to measure the temperature of the water that is coming back from the building. We're going to call that our chilled water return. And then it's also monitoring the temperature of the water that the chiller is then sending out as well. So that's our water supply. Basically, if it senses that the water is coming back too warm, what you're going to see is that the chiller is going to increase its cooling output by adjusting its compressor. So again, all of this is being signaled inside, whether or not this is from the manufacturer or whether or not this is inside of our larger control program. We'll talk about that in just a second. But again, it's just needing to be controlled. Once that water reaches the desired temperature, chiller is going to slow down to save energy. Same thing with our cooling tower. So once our temperature of the water is coming out of the chiller or coming to the chiller, you're basically sensing that temperature on both sides of it. If you're sensing that your water is too warm, your control system is going to start to speed up the cooling tower fans in order to blow more air and to cool that water faster. So again, all of this is just to say that, you're seeing how each one of these interdependent systems is working together to make sure that we're achieving that desired set point inside of a zone without using more energy than we actually need to. And the way that this is happening in this scenario is that all of that water is flowing through each one of these different areas, and you're seeing throughout, you're seeing water flow sensors. Is the water enough? Is it moving enough? Is the pressure enough? What is the temperature? And throughout this, you're always getting those little checks and balances to make sure that you're getting that desired temperature in those zones themselves. And again, if it is, then you want to be able to turn those off to save that electricity or to save that energy. The final piece of this that we're going to look at is something that's a little bit more applicable to real world, right? So this is a drawing that you actually might see out there in the field. And what this is awesome because Moose is going to take us through this tomorrow and actually build a real sequence of operations around this diagram. So what we're looking at here is going to be an air-cooled chiller. So we don't have the water cooling tower piece of this. So this is air-cooled only. And I want to give a special shout out to our friends at Sizer Co who provided me with this lovely control diagram here. But what we're going to be on the lookout for are going to be those inputs and outputs. Let's look through the components, whose responsibility these components actually are, and start to think about, again, how we can take our zone from the actual condition that's being monitored at the zone to that desired set point condition. So from the top left here, we're going to start at the chiller itself. So most likely, and I apologize if this is hard to see you guys, I will send this out too, and it'll be in PDF capability. So if you need to zoom in, you can. But what we're seeing up top there in a real diagram and a schematic like this one is the chiller itself, right? So you can see on there that the drawing indicates that this is going to come with a panel that's going to be interfaced via bacnet MSTP. And so that, again, we talked about those protocols in 102. So we need to make sure that whatever network we're communicating on in our whole system is also going to be able to talk to our packaged component, which is going to be that chiller. So we know that that's going to interface via our protocol of bacnet MSTP. So also here you might see Ethernet, you might see IP, depends on how it's talking to. It's just in this schematic, it's bacnet MSTP. And again, this is normally provided by the chiller manufacturer themselves. The next component on there is going to be a flow switch, also manufactured by the chiller manufacturer, but typically it's going to be wired up by the engineer. And next, we're continuing to move towards the right there. Sorry, this goes a lot better in person, so I can point to that diagram for you guys. But we're going to continue to move along, and we're going to get into our temperature sensors as well as our chilled water pumps, excuse me. So basically what we're looking at here is our chilled water pumps. It looks a little bit different than in that boiler diagram that we saw, because in this scenario, we don't have any VFDs on here. So right now, if you look down at the bottom, where we'll look at next, is that we're going to see that we're just looking at binary inputs and outputs on our pumps. All we're looking at is seeing if the motor starter is on, if the motor starter is off, or the status of that pump, whether or not it's on or off. And so that's what's really on that bottom level there. Again, you can see whether or not those are going to be inputs, outputs, whether or not they're going to be analog or digital. So as we look on here too, you'll see there's a couple of other just ancillary items. We're seeing there that there is going to be, a outside air temperature. So again, that's monitoring the outside air temperature. I think on there we see a couple of different temperature sensors. One is going to be on that chilled water supply, and one is going to be on the chilled water return. These are going to be our analog inputs, right? Because we need to be thinking about there's a range of values. So we're looking for more than just that binary on-off. We're looking for what that range of values actually is. So from a diagram like this, combined with our points list, we can really start to build in what we want this system to look at. So again, you see here, we're using an MSTP protocol. We're seeing that we have three analog inputs, one analog output, three binary or digital outputs, and two binary inputs. So essentially what we would need for a system like this is that we would need a controller with at least 5 inputs and 4 outputs that are all real, can be wired up to that controller. So really here you could be using, again, anything except for an application specific controller. So you could use a building controller, you could use an advanced application controller, but that application specific wouldn't really work in this scenario. So when we're going and planning about how this would work, you're going to say, okay, well, let's think about how this needs to connect to the rest of the system. Are we going to be scaling this system, or is this it? And if this is it, maybe that advanced application controller would be perfect. If we're thinking that we need to scale this bigger, maybe it's going to be a building controller. And again, this is where you start to think about, what type of interfacing you want. And that's where we're really going to start to drill down into that manufacturer specific. So, we have all of the capabilities to do this. You as engineers, you probably have all these capabilities as well. But that's really what we're working towards when we start talking about controller selection, when we see a diagram like this one. So this is just that same points list built up from that diagram that we saw. And again, these are really just here for resources for you guys to be able to kind of gut check yourself if it's, you're newer in this space, if you're not sure whether or not it needs to be an analog input, analog output, what you should actually be measuring on a chiller. This is a really good place to start. And what's cool about this is we're going to use this exact same example for tomorrow when we start out, and Moose will take us through being able to, create that full sequence of operations for something that is specific like this. So those are really it. Those are really the bread and butter of the mechanical systems that we're going to run into in some of these buildings. The final design considerations that I just want to end us on before we break for the evening. And then again, everybody can't sleep because you're so excited for BAS 104 like we are. Couple different considerations to start talking about when you are looking at, okay, now we know all of our mechanical systems. We know how we're going to start to control these things, but what else is involved? When you start talking through load calculations and zoning regulations and requirements, there are going to be certain things that you need in order to meet specific occupancy and environmental needs and standards, which again, we'll talk through I think we talked through that one in the building wellness presentation tomorrow. But just keep that in the back of your mind as well, is that there are specific load calculations that do go into this. And system redundancy is a big thing, right? So if something goes down, how are we going to continue to maintain that space, that resiliency, in order to, not have that temperature skyrocket or, whatever the case may be in system redundancy. And this is where we really get into things like having a lead and lag pump. And, there's just a lot of different ways that you can ensure and maintain system redundancy. So again, start to be thinking about some of these big kind of like these big topics when you are planning out your building automation system. And then that final piece on there is the sequence of operations itself, which is what we will be building with you guys in 104. This is what's really just going to outline all of those functional steps of a system to perform under specific conditions, which, truth be told, we really just talked through all of them, but we're going to go into and really see how this looks in the real world tomorrow. I know that was kind of a lot. I think we're right about at the 45-minute mark there. But that was it when it comes to BAS 103. If anybody has any questions, we're here for a little bit. I know, like I said, we're definitely coming on 5 o'clock for our Eastern friends. So if you guys need to hop off, you can. Tomorrow, I think we're going to start tomorrow at noon Eastern time with BAS 104. And like I talked about again in the beginning, we will be sending out a survey, and that is especially important. And again, I apologize for all of our technical errors, but it is especially important for if you would like a certificate of completion, we will need you to reply to that email. So if you don't get it, I'm also going to be putting up our contact info first thing tomorrow. So if you don't get that survey by the end of tomorrow, let us know. All of these presentations are going to be recorded. We will give you all of these presentations to kind of dive deeper into them, and feel free to reach out to us offline if you guys have specific questions on anything that you've seen here.
Awesome, Emily. That was a wonderful job. Thank you everyone for joining. We'll start. I'll see you guys in the morning, 104, 12 p.m. Eastern time. Grab a coffee, answer some emails until we get to you. So thank you, Emily.
No problem. I can't figure out how to stop sharing my screen, so I'm just going to end this meeting.
All right.
I am the source of all of our technology woes, everybody. I apologize.
Single point of failure.
Okay.
Go ahead, take it.
Thanks, everybody. We really appreciate it. We'll see you guys tomorrow, hopefully.
Take care. Bye, Emily. See you, everyone.
Okay, how do I stop this recording? There we go.
The recording is stopped.
Got it.